Okay, let's do it. We are recording. We are recording. Anyway, for those of you, okay, so one quick thing in case you want to, help us out during the workshop. We totally understand your privacy, so don't worry if you feel uncomfortable. So it just helps us that we're not talking to a gray screen. You don't have to unmute yourself, but if you have the opportunity, just turn on your webcam so it makes us feel a little bit better. So again, no requirement. But
It's good
thank you so
to
much.
see some known faces.
Yeah. So it makes you can see us, but it makes us a little happier to see old friends and new ones too. So anyway, thank you all for stopping by. And today we're going to continue kind of the journey that we started last week with feature finding. And so one of the pitfalls with feature finding is you see the same molecule repeated with different adduct forms across your LCMS. Muting. And so that increases the complexity. And so that's not particularly great if you want to reduce kind of your data and really start exploring it. So one of the things that is pioneered by Allegra, Danny, and Robin, and I didn't do anything, I just kind of hang out. And what they've been doing is trying to build into MZMind, as well as working with the rest of the community to build into other feature finding tools, the thing called ion identity networks. So it really helps visualize your data better, connect it using LCMS feature information in a more intelligent way. And we want to show you today how to use it and how it integrates with feature-based molecular networking in GNPS. So hopefully it'll be seamless and kind of interesting to use, as well as kind of really cool visualizations that Robin put together. Anyway, so without further ado, and because I don't actually know anything, I'll hand it over to Danny, Robin, and Allegra to show you how it all works.
All right. Yeah, like good morning or good afternoon or good evening, everybody. Yeah, it's great that you all stopped by again, and it's yeah, like a pleasure to do this with Allegra and Robin, and to give you like a little side story how that actually all started. That was also during a GNPS workshop, because we met Robin 2 years ago at the workshop we gave in Germany, and then we joined forces, and Robin stopped by in San Diego for a couple of months, and that's when basically ion identity networking was built. So yeah, it's a lot of fun to be here and to start. And I just wanted to like give you a recap what basically Ming already just told you a second ago. That like last week we showed you feature-based molecular networking, which yeah, it's like an alternative approach to classical molecular networking, which was introduced a couple of weeks ago, where we make use of feature finding tools to actually work with extracted ion chromatograms and link those to MS2 spectra for molecular networks. And we gave you a little hands-on task last week to actually mine native mass spectrometry data, where we infused like post-columns some metals. And hopefully we could make the point that we can induce now metal binding for like Siderophores in that data set, but those compounds were like located at different spots inside of the molecular network. So that's the example network we had. And yeah, when we look at the different ion adducts, we could see that actually here the orange ones, so the iron adducts were like farther away from the M+H version of these molecules, or for another case, there was like an M+H, and then here from the very same molecule, we had a sodium cluster that was like elsewhere in the network. And that's kind of like a little bit like a bottleneck of molecular networking. And the reason for that is very simple. When we look at the MS2 spectra of those, due to different like charge energy through a different adducts, they fragment slightly different in collision-induced dissociation. And hence, like molecular networking and the cosine similarity metric simply will not bring them together. So yeah, what we want to like show you today is how we can bypass that by actually looking at feature correlation and stringing them together on an MS1 level. And that makes basically use that like the same compound has the same retention time, whether it's like a sodium or a protonated version. And then if we would look at the very same network, we would see that now indeed we can pair them through like an orthogonal edge. So that's an ion identity edge, like a dashed line for both the iron and the sodium cluster, plus any other possible adducts or yeah, like in-source fragments whatsoever. We just released a preprint for that. So if you're excited about that and want to like read a little bit more in detail, I would encourage you to take a look at bioRxiv. We just deposited it last week. So yeah, it's really brand new, and yeah, it's a lot of fun to show this today. So yeah, we're going to use MZMine, and it's very much the same as we did during feature-based molecular networking. The only thing is now we have here this new red box, which is the ion identity networking step. So that consists of 2 modules, which Robin will talk about in detail in a second. And in addition to that, whereas last week we went through all these modules step for step, what we're going to do today to make this a little faster is we're going to use the batch mode of MZMine, which besides ion identity networking, if you don't know it already, might be very useful for yeah, like a more efficient data processing. So yeah, thanks again for stopping by, and I give over to Robin to walk you through.
Hey, thanks, Daniel. And yeah, thanks. I'm very happy that I can be with you today from the German outback, where the internet is very bad, but it seems to work. So I'm going to try to share my screen. Let's see. All right. And so I think you all must have been in this document here in the Google Docs, where you can see all the different steps that you had to do for the participation or for preparing yourself. And I just want to remind you, this workflow is currently only available in a special version of MZMine. We are currently working together with Tomasz Pluskal from MZMine to create MZMine 3. And in this version, we will have the ion identity networking integrated, but it's a very big structural change. And so right now, you have to go and visit this website, download the release, and then I'm going to show you again how you can download data from Massive. I hope you all have downloaded the MZML files that we provided. And we have the results of the example job. So if anything fails, we have a safeguard for you. You can just go here and later get the GNPS results from this website here. And so I hope you all found a way to download the Massive files. Can you see all my screen? Because I have so many pop-ups here. Fine, okay. So for me, it was sometimes confusing to download things from Massive, but it's actually pretty easy. On a Windows computer, you can just paste the link. So you could just go FTP and so on, paste the link and the Massive ID here. You can download the MZML files from the peak folder here. And in the other folder, you're going to find the files that we create in this workflow and upload to GNPS to run ion identity molecular networking. And you're going to find the MZMine batch file. And this is very important. We need this batch file because in this batch file, we have all the different steps. We have all the parameters that we're going to use to run ion identity molecular networking here. So please download this batch file and also make sure to download the metadata file. And then we're all ready to go. And to open MZMine, so you've downloaded the special version and you open the folder of MZMine. And here you have platform-specific run scripts. So we have the Windows version, Mac, and Linux. You just start MZMine now, and you don't need to import the raw data because we're going to do this in the batch mode. So I already did this here. And So I already did this here. So I have MZMine open, and I hope that all of you can follow, and that all of you have opened this version. And I'm just gonna show you, you just go on project, batch mode. And here in the batch mode, we're gonna import the batch file from the massive folder. And I think Daniel shared this with you, the PDF with all the steps, did you?
Yes, I did. The link is in the Google document.
Yeah, so I'm going to walk you through in MZMine, but in this PDF, you also have all the different steps and all the parameters again. And so we just open batch mode. So again, we go on project, open batch mode. And then we just click on load. And I have the folder here. And then we just open the MZMine iron batch XML and replace or anything. And it is always nice if you use MZMine. It's always nice to perform the steps on the data set that you just acquired. It's always nice to optimize the steps step by step. And then I usually go through all the modules from the menu. But if you already have your method, it's good to set up your batch here. And then the only thing that you have to do is first you have to change the raw data import. So we go on configure for the raw data import. We select the raw data files, the MZML files provided in the massive folder. And then most of the other steps are actually fine. And we only have to fine tune the last one. But so you select the raw data files, and what MZMine will do is it will run mass detection and the just normal feature finding workflow that you can also see in Daniel's video on YouTube, or that you can see from the feature-based molecular networking workflow. And then at the end, we now have a few more modules that we are going to apply. So, and the first module is meta-correlate, which is a correlation algorithm that's going to group features from the same molecule. And so it's going to look at the retention, at the feature shape, and then group all the different ions, sodiated and protonated and so on. So we're going to go, I'm not going to go through all the parameters, and Daniel is going to show you what it actually does, and it's going to visualize it a bit better with some graphics. And so we're just going to stick with the parameters here. Basically, what we're going to do with this module is we look in the retention time window, and if we see two features in the same retention time window, we try to correlate the feature shape and group them based on this. And in the second step, we're going to try to find an explanation for the MZ delta. And I hope that you all followed me here. So if you have any questions, you can always type in the chat, and the others will try to answer and try to stop me if it's too fast or if you have any questions. And so ion identity networking is then the module that's going to actually annotate the different, or identify the different ion species. So in here, we have the MZ tolerance. We are going to only do it for features above this height. And the most important thing is the ion identity library. And as we are working here on a special data set, so in this data set, we are not very interested only in the like standard adducts and ion species. We're also interested in iron adducts. So we want to find molecules that bind iron by post-column infusion. And so if you open this up, you're going to see we have just selected the standard adducts here. Basically, we have then a specific iron adduct where we lose 2 protons and we add 1 iron. And on the right side, you're going to see we have neutral modifications. So the right side is to add some in-source clusters, for example, with formic acid here, or some in-source fragments like water losses or something else. So if you, later on, if you want to know more about how you can add adducts or modifications and how you can run the whole thing, we also have some YouTube videos that I'm going to put into the Google Doc. And here I'm just going to show you, you can basically go on add, and then you could type in something like sodium, and it's going to, I clicked on something here. It's just going to add sodium to the list down here. So if you type in anything, for example, now we have iron. If we're also interested in zinc or in copper, we could just type in copper and it's going to pick up here and like this. Okay, but we're going to stick with the parameters here. And then the last step is export and submit to GNPS. With this module, you can basically create all the inputs that you need for feature-based molecular networking and that you need for ion identity molecular networking straight away. So what it does is it's going to export the quantification table for the feature list, and it's going to export the spectral summary file, so 1 MS2 spectrum per feature, and then we have the option to directly submit it to GNPS or just put it in a folder and we can do it manually. For this workshop, we plan to do it automatically. So please just open the export and submit function here. So we go on configure, and we have to change a few things here. First of all, you have to change the file name. So you basically have to find a folder where you want to put the results. So for me, I have a folder here, GNPS, and of course a file name, workshop. Okay, and then we need to set up the submission to GNPS. So in this step, this is totally optional. You don't have to do it. But if you click on it, you're going to see we have the option to add a metadata file. And we have a job title, username, and password, and we just have to set it up here. First of all, you can select the metadata file that was supplied in the massive data set. So we go again on and select the file metadata workshop.txt. And then I think the name is fine. You can change it if you want to. And then we can type in username and password. And if you don't have a username, I mean, I definitely encourage you to go and sign up on GNPS and do this, because then the job will be submitted in your private user space. If you don't submit with the username and password, it's just going to be a generic job that you can later copy into your user space. But you can either type in your username and password, or you can copy it later. And then, of course, we can type in our email address. So if the job is finished, we're going to get a notification by email. And with this, we've set up the whole thing, and we can just go and click OK. And now we can run it. I hope that everyone has got to this point. And so if you set up the raw data import, and if you've set up the export and submit to GNPS, we can now just go and click on run.
Hey, Robin.
So, yeah.
Thanks. There were a couple of questions, and thanks for repeating actually that last step. So, and I think one very important one was whether those settings need to be all set right now, or whether people just need to run that batch. And just to repeat, so what you need to adjust is actually the raw data import module, because you need to specify where those files are located on your computer with the correct file path.
Yeah.
Maybe Robin, you can just like show it in a second again. And then the last one is the export for and submit to GNPS module, because also there you need to like define your user specific information. So that's the login information as well as the location of the metadata file. So Robin, if you could like just repeat those.
Yeah, so otherwise you will get some errors by mzmine. So first of all, definitely specify the raw data files on your computer, because I've put them on a folder on the desktop, like a professional. And so you just select all the raw data files here and click on open. It's not going to open it because it's in the batch mode. So all the steps are going to be executed step by step. And if it fails like halfway through, we can like reset the thing and run it again. But it's good if it runs directly, right? So we set up the raw data import. We only have to now specify the destination of the results. So first of all, we have to specify the file name, and you just go and select the folder, give it a file name, and then you should be fine to go. And then you click on submit to GNPS. So there's this one's checked. And on the setup, we can basically specify the metadata file. And the metadata file in GNPS is basically sample grouping. So we have some samples with a different treating or different conditions. And so this is a metadata file that you have to supply here. And we have to check the box. And then we're just going to give it a title. Username, password is optional, but is definitely good. If you have a username and password, you should type them in. And then we use our email if we want to get notified if the job is completed. And with this, we just close the window. You can actually, if you want to, you can click this one, and then the folder is going to pop up and going to show the files that we export directly after exporting them. And with this, we're ready to go. And if I click OK, it's going to import the raw data files. It's going to do mass detection. It's going to do chromatogram building, and so on. And it's going to find all the different iron species.
Robin, before you submit it, we got another question here in the chat, or actually two questions, which we're asking both the same. And so they were dedicated at gap filling. So in this particular batch, the experienced user probably has noticed that we did not include a gap filling step. So without going into detail why we did not do that here, or for what type of like data analysis this is appropriate, maybe you want to highlight really quick if you would want to like add the gap filling step into that batch. So how you actually modify that batch file.
Yeah, so if you would like to incorporate the gap filling, so we would definitely add it somewhere after the alignment. So gap filling is, we do feature finding here in one step, right? Or in multiple steps, but we do the feature finding, we find chromatographic features, and then, but we're not perfect. And so gap filling is basically a second step of feature finding to find features that we might have missed. And if you want to add any step to this batch, you just go here, and I have to find it. It's somewhere processing.
It was a little up, I think.
Yeah. Oh yeah, right. So, and then you have gap filling, and there's different options. I usually go with the Peak Finder multi-threaded because it's fast and it's good. And so basically here, of course, I'm not going to go through the details, but it's basically the feature, shape, kind of filter, and then MZ tolerance and retention time. And we're just going to edit, and then I can just pull it at the destination where I want to have it, either here after join alignment or either after filtering for features that have an isotope pattern. So that's basically the peaked list row filter here. And if I don't want it, I'm going to remove it and we're fine. Gap filling is definitely good if you want to do statistics and so on. It's definitely needed, I would say. It's very hard sometimes, and it really depends on the data set and on the analysis. But yeah, like for this small data set and for the workshop, we're not going to go with gap filling here. Okay, I think we're fine to go. If you have any questions, you can also ask me afterwards. I'm just going to click on OK, and we're going to run it. And I hope that everyone is following. And oh, wait. OK. In this version, we need the username. Since when? I programmed this, and it seems like we need the username and password. It's pretty funny. Okay, so basically, at one point it was optional, but I don't know why we changed it. So basically, if you got the same thing, same error, you just go on configure, setup, and you need to supply a username and password. And if you can't supply your username and password because you have forgotten, or you are not a user on GNPS, which is a pity, and you should sign up, you can just go ahead and uncheck the submission to GNPS, and then you have to do it manually, just manually, like for feature-based molecular networking. Okay, so now we're going to try again. It's going to ask me if I want to remove the prefix of the raw data files because it detected that the raw data files always start with the same name. I'm going to keep them. And yeah, now we see that we have the different steps running here. It's going to import the raw data files and then afterwards it's going to do all the different steps that we asked to do. So any questions from the chat? I hope that it runs for everyone. So,
yeah, so there was one question why we did not do gap filling here in particular. So
here in particular.
Want to go into that now or later in the breakout room?
We can do it later in the breakout room, but I mean, we also have some time here. I think first of all, we're not going to apply statistics and really need the I don't know, like values all to be as correct as possible. But I think in this case, it's a very small data set and the features are fine. So feature finding should work out fine. And yeah, I don't know. Maybe this was the reason here. Usually,
so also to keep it simple, we decided not to do that. So I already answered it in the chat. So gap filling is great, but it also comes with a disadvantage, and that is that it actually fills in more noise. So if you look at your feature table on a binary fashion, so present, absence, then you will probably detect most of the features, although if they were not present. So the proper way to deal with that would be to apply a post-feature finding cutoff. And that were all things we didn't want to deal with in the workshop. But yeah, if you would have a large scale data set and you want to do statistics, then I would probably recommend you to do gap filling.
Yeah, I think usually I use gap filling, and but then afterwards I just specify more filters for the feature shapes. So I would then go and let's say define. I definitely need 3 data points on the feature and so on. So yeah, we just skip this here. And yeah, for me it already finished. So you might have seen it did the feature, the mass detection, and now we have the check marks here because all MS1 scans have mass detection run on them. And now we have the chromatograms and deconvoluted chromatograms, de-isotoped, and aligned feature lists, and so on. And this is basically the result of meta-correlate and ion identity networking. So basically, this feature table here, we send this feature table to GNPS now, and it has some extra information. So it has some additional information when compared to feature-based molecular networking, as in the different ion species for different molecules. And so you can see it here in the table. But we gonna visualize this later in Cytoscape when we download it from GNPS. So the results are here. It actually popped up. So we have the spectral summary file with all the MS2 spectra in it. We have one quantification tables, the feature table that we exported, and it's actually the last feature table in the list of feature tables. And then we have some additional edges, and these additional edges are created by ion identity networking and the correlation of features, and they describe the different ions that we're going to see in Cytoscape later. And it also popped up the job. So we see I logged in with my user, so it's in my personal space. We have here the title, and we have all the different files. We have the metadata sheet that we've uploaded. And if you now see that you don't have the metadata sheet, I would suggest that you just go and rerun the submission to GNPS maybe with the metadata sheet. Or you can just go on clone or go on clone to the latest version. And then you can fill in the metadata sheet here in the screen. And I have to log in. Okay. Oh, it's everywhere.
All right, thanks a lot, Robin, for walking us through there. Just like to get a little overview, who managed to run that batch and to automatically submit their jobs to GNPS? Can we get some thumbs up from the audience? Or no buttons if you had problems? Okay, I see some check marks. One thumb up. Okay. The others are still working on it, or is it still processing? Okay, some people had problems with the pace. So okay. Yeah, maybe just like to recap really quickly, all you needed to do was to load that batch and adjust the file path in the first and the last module. So raw data import, make sure to configure the file path. So if you hit configure, Robin is doing it right now for you. Then specify the file path. And then in the very, exactly. And then in the very last module, configure, you have to specify the file names. And then when you go to the setup for GNPS, you have to specify your username, password, email, as well as the metadata sheet. So there at the very top, there's the metadata file. So here you also just need to put a check mark and yeah, basically specify the file path. And that's all you need to do. Then it's just okay. And then everything should be done by the batch. So yeah, I guess in order to keep on track, we probably keep going in a second, unless there was some like major hiccups in that batch. And if you did not make it so far, we also got you covered because we already pre-submitted the GNPS job before. So the next step, which Allegra is gonna talk about in a second, the download and Cytoscape visualization, you can simply start from yeah, that already processed job. So it would be, of course, great if you can keep going on from your own job, but that also is going to take probably like 15 minutes or so. So in the meantime, if Robin lets me share my screen.
Yeah.
All right. Yeah, I just want to recap like a little bit what we just did. So, and I actually want to start here. And that is the data acquisition of the data we were just working with. So we used a UHPLC QExactive coupled system where we first separate those compounds and then analyze them by tandem mass spectrometry in an Orbitrap analyzer. And I assume that most of you know that how that data was acquired was data-dependent acquisition mode, which is probably like the most common MS technique for non-targeted metabolomics right now, where the machine walks through so-called duty cycles where it acquires an MS1 scan and then based on this information picks the most abundant peaks and acquires MS2 scans in an iterative fashion. So in our case, it was a top 5 scan. So we actually acquired 5 MS2s from a given precursor scan. So now what classical molecular networking would do is that it would only look at the MS2. So like all MS1 survey scans, they are not used. And we only like do data analysis on MS2 level. Feature-based molecular networking now instead actually makes use of this MS1 scans. And it constructs, after peak picking, so that was the first step, it constructs extracted ion chromatograms on MS1 information. And then we get, yeah, basically chromatographic peaks. And then in the deconvolution and pairing step, we investigate those extracted ion chromatograms and check whether there was an MS2 spectra triggered within that peak window. And then we simply assign those MS2 spectra to a given feature. And then over a data set, we can compare those different extracted ion chromatograms, like in the, you can see here on the right, between samples, and like compare their relative quantities to each other. So now with ion identity networking, we basically make use of all that infrastructure. But what we now do is that we basically also align extracted ion chromatograms from different features based on specific mass deltas that are user defined, which we defined in the ion identity networking module. And yeah, so if we now look basically at different features with like different delta masses, so we can basically ask the question, okay, do those peak shapes correlate? And then we simply do like a Pearson correlation, or we could also do Spearman, but either way, we start establishing a link between peak shape. And that's actually something which has been done since like a long time and on a like very manual level, like analytical chemists. It's a very typical thing to do and investigate your data whether like an adduct has the same peak shape. So now what that allows us is to, based on this user-defined mass list, to actually identify the different adducts. And not only adducts, we can also look for neutral losses. There was actually a question about that, and look for potential in-source fragments. And the advantage here is that this is actually done on a systematic fashion within our workflow. And then we can simply combine this information together with the molecular network. And in a second, Allegra will show you how to actually visualize this in Cytoscape. So in this case here, we have the blue edges, which means that two nodes are similar based on their MS2 spectra. And then the red dashed nodes are actually based on correlation. So they tell you, okay, this is a co-eluding feature with one of the allowed delta masses. And then, yeah, we can identify, for example, like a sodium adduct and so on. And yeah, as I said earlier, we have the same data set as we used last week for the feature-based molecular networking workshop. So yeah, we basically cultured E. coli Nissl and did native electrospray functional metabolomics experiments. So if you're interested in the science behind that, there's this preprint you can take a look at. And what we did here is that we artificially induced post-column metal binding. And yeah, so for the remaining of the workshop, we're gonna like now go after the challenge to actually identify bound and non-bound siderophores. So in this case, we had like iron addition experiments. And then yeah, we're excited to see what compounds you will come up with. So I guess at that point, Allegra is gonna take over and walk you through the download and visualization in Cytoscape.
Okay, cool. Thanks, Daniel. So hi, everyone. Yeah, so I think most of you guys hopefully were at the previous two workshops on feature-based molecular networking, because now what we're going to do is we're going to basically turn to the like hands-on activity where we're actually going to look for those new and previously known siderophores. And so we've kind of been working up from last week to this point. So hopefully you guys are excited. So now I'm going to share my screen with you guys. So yeah, as previously, going through the Cytoscape is all detailed in the slides. So if you get lost, I would suggest going to the slides, but I'm just going to go through it on my screen. So yeah, hopefully that works for everyone. Let me pull this up. Okay. All right, so can everyone, let's see, can everyone now see my screen? Yeah?
Maybe you can zoom in a bit.
Okay. Is that better?
Yes, good for me.
Okay, great. Okay, cool. So yeah, so now I've just clicked on the job link that we provided in the Zoom document. And so now we're going to go to Cytoscape. So so remember from last week, there's two different ways to download files from Cytoscape. So we can either use this, export or download network files, or we could do this direct download. So I'm going to start with this direct download because one really neat thing about doing the direct download is that there's actually some templates that are available for your use. So last week we kind of went through Cytoscape and showed you how to change like node colors, node shapes, edge widths, etc. But let's say you have a template that you really like using. You can actually add that as a style. And so then you can actually just do a direct download into that style. And so I have one that I like, and it's called this ion identity. So we can pull that up and then just do the direct download of the Cytoscape file. So that is downloading. And now we can open it. So give me a minute while it opens. All right, can you guys see the Cytoscape now? Okay, cool. I've been doing these Zoom workshops on only my laptop, but now I have my two screens. So I'm just trying to make sure that I'm sharing the correct screen. Because yeah. Okay, so great. Okay, so now what we can do is for some reason we're not really seeing the nodes. And so I think this is, the size there might be something sort of off with the size. So I just kind of went down into the little drop down and I deleted the setting that was there. And so now we can see all of our nodes. And so, yeah, so here's our nice network. And so now we're thinking about, so our question is, what Siderophores are present in this network? And so I think a good way to try to answer that question is to do a few things. So first off, it would be really nice if we could color those nodes that have been sort of chosen to be the iron adducts. We could color those with a specific color so that they pop out. And so the reason that I like this presetting or this preset style is because that's actually what I've done. So we can go in to this fill color, and we can choose under the column, we can actually choose this best ion. And now we can go into discrete mapping, and we have all of these options for different adducts, okay? And so, so we're interested in iron, in the iron adduct. So we can color that orange. And then let's say we're also interested in the 2M plus iron minus 2H. This is going to be like the dimer. We can color that like yellow. Okay, cool. And so now this draws our attention to some of the compounds that may be binding. Okay, so from there now, I think the next thing I might want to do is actually look at the different edges, because this is really one of the things that we've added with ion identity networking. In addition to seeing the MS2 similarity edges scored with the cosine score, like we usually see when we do molecular networking, we now have an additional set of edges, and these are corresponding to MS1 deltas. So the differences in ions, the MZ differences in ions. And so in order to start investigating the edges, we can, remember, go down here to this edge button. And then the first thing I'd like to do is basically specify that we want a standard cosine score edge and then an MS1 edge to actually look different. So we can go to line type. And again, another reason why I chose this template is because we've set that. So now we can go to edge type. And again, discrete mapping allows us to actually define the different mapping types. And so for the cosine edges, we'll keep that as a solid line. And then, oops. And then the MS1 annotation edge, we'll do that as a dash line. And so now we can look, and so here, for example, is a dashed line. Here is a dashed line, but then we also see solid lines. And so you might notice actually when we look at this network that now that we've incorporated ion identity networking, we actually see significantly more connectivity in the network than we had previously, which is really interesting because it sort of shows us that a lot of maybe many of the singletons are actually ion adducts. And that's really nice because in addition to allowing us to find siderophores, we can also start to understand many more of the compounds present in our samples. Okay, so now let's color some of the edges based on the specific mass deltas of those edges. So now we can go to stroke color, and again, you'll always just click on this arrow to make changes. And now if we go to the edge annotation, that actually is going to be describing basically the identity of each edge. And so here, these are going to be the cosine edges. But then if we continue scrolling down, then we start to see, I'm going to make this bigger so everyone can see. Then we start to see edges that correspond actually to mass deltas in the MS1. And so now, for example, we can actually start to color edges that correspond to iron adducts. And so here we see, for example, this edge corresponds to the difference between a 2M plus iron minus 2H and a 2M plus H. So basically the dimer, and then the dimer plus iron. And so we can color that just by clicking here. And yeah, we can color that orange, for example. I didn't see where that popped up, but we can continue to go through and color those iron binding edges. And so now you can see, for example, actually that one may have already been there, but we can continue going through, and I'm not going to do this for all of them, but okay, so yeah, now we see we have some orange dashed edges, and so those are likely, well, those are corresponding to iron adducts, and so it makes sense that we have an orange dashed edge connected to the node that has been annotated to be an iron adduct. And then if we want to make our network look nicer, for example, just to review some basics in Cytoscape, we can, let's say we want to make those apo or unbound Siderophores pop out, we can actually highlight that molecule, go back to the node, and then we can give them their own color. And remember, in order to do that, you can now go to this bypass filter. And for example, we can color them like this one purple. And if we were interested, we could just go through our network and just do this to some of the other apo versions of the Siderophores. So yeah, I think for now that was pretty much what I wanted to cover for Cytoscape visualization. I think you get a pretty good picture of how if you kind of just organize and color code your network, you can actually visually inspect it, and these molecules, the Siderophores present in this data set, really just start to pop out of the page, and it's very obvious to find them. And so that was kind of what we were going for when we were developing this method, was just like a high throughput way of sort of easily finding compounds with some function of interest. And so that's why we've called this like a functional metabolomics approach. And in this case, we're specifically looking at metal binding compounds. So I think that's all for now, except we're going to go into breakout rooms. And so I just want to remind you that I think it would be really nice if in our breakout rooms, everyone can see my PowerPoint slide? Yeah, so in our breakout rooms, we would really like you guys to sort of go through what we've discussed in Cytoscape and find the potential Siderophores in our data set, and then see if we can start to annotate these molecules. And so this question will, or these two questions, I think, bring together the last 3 or so workshops, but also some of the previous workshops, because in thinking about annotating some of these molecules, we might actually want to go back into GNPS and do some in-browser visualizations and explore some mirror plots. And so I think hopefully you'll be able to synthesize a lot of the information that you've learned. And hopefully, yeah, I think we have a little more time for the breakout room this time. And so hopefully that'll be useful for everyone. So
awesome. Thanks
yeah.
a lot,
Thanks,
Allegra.
Yeah.
And before we split into smaller groups, also just to give you like a teaser. So the information from the ion identity networks, where we basically know like part of like the elemental composition, because we know, oh, that contains a sodium or that contains an iron. That of course like can also be leveraged for other tools in terms of annotation. So here, for example, molecular formula calculation, whether simply by exact mass or by fragmentation trees with Sirius or Zodiac, can make use of that information. So there's a bunch of tools that we now interface that also might be introduced in future workshops in the next couple of weeks, actually leverage that information. So yeah, I hope you got excited about it. I hope you have like all these networks in front of you now, and we can actually explore a little bit the chemical space of E. coli and Nissl.
I would just, because of the question that came up, I would just like to show the GNPS job website once more. So can I share my screen? So basically, there was a question if we can directly compare it to feature-based molecular networking. And of course, if you have the job from the last workshop, from the feature-based molecular networking workshop, you can use this. Or we could just go and clone the job. So basically, we clone to the latest version, or we clone. And here we're going to see what's the main difference. So first of all, the difference is the quantification table has more metadata. So we have more information on the different ion species, and more information from the feature finding tool is provided. And then we also have the additional edges file. And so you saw that here we had 4 different files. And if it does copy the job, maybe I should have done it before. I told you I'm in the German outback. No internet. Okay, yeah, it doesn't clone. So, but the idea is in the feature-based molecular networking job, you usually just select the different. Okay, it's here. Oh no. Okay, it was there. So you basically select the different files, and here you have, for ion identity molecular networking, you have one more file, which is just right at the bottom with advanced tools. And you can just deselect it, run the job again, and then you basically have similar results to feature-based molecular networking, just from the connection. Because of course, the molecular networking edges are still from feature-based molecular networking. Okay, so I'm going to stop it because it doesn't seem to work.
Cool.
Okay.
All right, then I'll see you in a second in the breakout rooms.
Oh, real quick. Don't look at the last slides of the PDF maybe until after the breakout rooms, because those are, unless you've already looked at them, they sort of provide, well, some of the answers. So, yeah.
Hey, everybody.
Hi, I'm eating a giant pizza, so I'm going to shut off my camera again, so you don't have to watch this.
At least we can't smell it.
Yeah, maybe that's better.
All right. Do you all have networks in front of you? Did you identify some Siderophores?
So I don't, but I still have a question. I'm still not sure I fully understand when IM molecular networking is making a network. How is it balancing the MS1s versus the cosine scores, the mass differences between MS1s and the cosine scores?
So this is just an additional information. So if like two nodes share both like a similar MS2 spectra as well as co-elude and have a defined delta, like a water loss from an in-source fragment. So then you will simply see that there will be two edges in the molecular network. So they don't compete against each other, they just add on. So actually in the, let me see if I find an example in my network here. Yeah. Okay, share my screen. So this case here, you have both like the dashed edge as well as a solid blue one. So that would mean that they co-elude as well as have a similar MS2 spectra. I would assume that that might be like an ammonia loss. Yeah, I think that.
Okay, that makes sense. Thank you.
Okay.
So this, I don't know if you guys are going to cover this or not, and whether it's a bad idea or not, but seems to me like you would want to merge all of those for quantification, possibly.
Yes. Yes. So to collapse, you mean?
Yeah.
Yeah, that's a very interesting point. We can actually do that. I think there is a function in ion identity networking. Let me.
So I think it's kind of the most simple operation you can think about is addition, but it doesn't particularly make sense because the ionization, like if you have a molecule coming in, the N plus H versus the N plus sodium, they're going to be relatively different, like ion counts in the mass spectrometer. So adding it is probably not the right approach. But merging it in an intelligent way is probably where you want to go. So if you can kind of treat them separately, but understand the statistics together, especially if they're going in the same direction, right? So that's probably, at least in my opinion, a better way to go about it. I mean, you can merge it. I mean, it probably just simplifies it. But maybe the better way to do that is just pick one quant out of the set of different adducts as opposed to actually doing an addition. So it's one of those things.
So are you saying more in a way you would just only retain the M plus H's for everything?
You could. I mean, that's one option for simplicity's sake, right? The kind of the first goal here is kind of simplify the data analysis a little bit. And the simplest approach is to throw away data that you believe is redundant to some extent. So if it's correlating across the samples as well as the retention time in abundance, then you're kind of enriching for redundant information. So you could throw away some of the information. That's unsatisfying in some ways, but additionally, what you could do is start asking the question across your conditions. Do all the adducts have the same sort of p-values or just general pattern? It should, just by definition. That's why we're grouping it. But yeah, the simplest way is just throw away everything except the most abundant, which is in a lot of cases probably N plus H.
Well, in any case, for quantification, you need to to do that for the calibration curve?
Yes, yes. You need a you can't cross-analyze, right, for the calibration curve.
Yeah, so maybe to like add on that from a technical perspective. So what we showed you today, that was like the very light version of ion identity networking, was like the minimum requirements. So that's the meta-correlate function and then the ion identity library. But when you like open MZMine and go to the, oh, let me share my screen. So when you go to the identification and then ion identity networks, you will see that there's actually a lot of different modules you can use to kind of like refine this interactions. So, and then from there, yeah, you can like collapse them either. I think there was at some point a function, I couldn't like ad hoc recall it, but you can definitely use the ID of the ion identity network in your feature table and like downstream, like align those together. So yeah, I definitely encourage you to explore this a little, especially like iterative refinement seems to be efficient to actually add more annotations into the ion identity network. And it's like, we didn't like go talk about like crazy adduct and clusters, but it's amazing how much actual, yeah, like redundancy of different adducts as well as like, yeah, like multiple M's, so multiple clusters, they are in your LCMS data. So yeah, feel free to explore it.
So to follow up on that, have you tried to use this ion molecular networking to link positive and negative ion mode data with different adducts?
Yes, yes, I think that's a very interesting application. I'm sure Ming is gonna tell in a second also about a standalone function in GNPS that does that. But yeah, obviously, if you have like polarity switching from like the same run, that would be like a perfect like application to merge that. We, due to like scan speed, I do not like to do that. Also, I don't know if you're an Orbitrap user, I think the board burns pretty quickly if you do polarity switching, but I don't know, it's just on a side note. So if you run them in two different runs and they're like after each other, then you can also do that. So you can do the correlation within the same sample, but you can also do them over an actual data set.
So the one issue that you'll run into, I don't know if this is handled already, is if you run into two different data sets, you have to understand which two files are from the same sample. So that's extra metadata you'll have to kind of link in there. Or else, I mean, it's all data, right? So then you have no idea when it will actually correlate. So that's kind of one of the limitations. As Danny said, we do other things that are standalone beyond that. So if you run your positive network and your negative network, we can link the two just kind of in GNPS, agnostic of the feature finding. Again, it's less powerful because you don't have all of the chromatogram information right then. So it'll be a less sensitive operation. But on the flip side of that, it is way simpler. So these are the inherent trade-offs. So it's kind of striking a balance between what your problem is.
So is that already available in GNPS or is that coming?
Yeah, so it's available now, actually. So okay. If you go to the tool index, because we built this thing because I sure as hell can't find anything on GNPS. I don't know how other people do it. So let me just link that really quick.
Just keep cloning everything.
It's still a work in progress. You know, as you can see, there's like a bunch of to-dos because there's like so many things we got to put in there. But under the tools, there is a merge network polarity somewhere. Yeah, merge polarity networks. So there's link outs to that. It's as simple as if you run your positive and negative network, you can put the tasks in from GNPS and it'll just pull all the data and just create you a graph ML that you can explore. We're rolling out a new version soon. We need to publish the paper. It's still pending. You know how it is. And allowing you to adjust some of these options like MZ tolerance, PPM tolerance, retention time tolerance. So that's kind of coming out in release 22. But at the end of the day, one of the things we offer is like try to do an evaluation of how well it's working. If you have library IDs comparing the structures, things like that. So figuring it out, let us know if it's useful. It's kind of better having one network than two in some cases, but different tools for different problems.
Yes, it is. Let me ask you a question about that. When you're doing the IO identity or this merge positive and negative, how the library match is done? With the ions or with the neutral mass?
So Dan, you can answer this
one. So they would maintain their like different nodes, right? They would just be connected. So you don't really like collapse them, which actually is awesome, because then if both MS2 spectra tell you the same ID or the same molecular formula, then you gain like confidence.
Confidence, yeah. Okay, but when you merge the positive and negative, just because I tried yesterday, you merge them and there is another library matching column. I don't know. This is imported from the original positive and negative, or?
Yeah. So I mean, it's a very simple operation. What we're doing, it really is nothing fancy. So it all comes from your original job. So all these library identifications. But what we do after the fact is, given those library identifications and those structures, you ask if they're concordant. So if you see, we suspect there's a molecule in positive and negative mode, that's the same. We ignore the structure when we make that call, but then after the fact, we evaluate that dynamically based on your data. So it's one way to, if everything just doesn't match in terms of structure, we know we're doing something wrong. But if they do, we hope that we're doing something right. So yeah.
So I have a question about the adducts. I have to specify what are the adducts, like the possible adducts that I would see, right?
Yes.
And also can I add multiply charged ions, like 2m minus a plus h? And for in silico fragments.
Yeah. Thanks for bringing this up. So like, again, we did like the very minimal version here right now, but there you really have like all the possibilities to form like user specific adducts. So I don't know if you maybe look for new gold binders or whatsoever, but you can like all like add those deltas. And just like, let me show you in a second here how you can define those, because Robin did not show this during the workshop. So if you go to identification and then ion identity networks and then ion identity networking, there's like the settings, and yeah, we had those all preset from the batch. So that gives you a good starting point. But if you now wanna like specify something, then you can go to the ion identity library, and then this new window here will pop up, and you have like two fields. So adducts on the left, and then modifications for the right. So that would be neutral losses. And then you see that there's already like a bunch of like opportunities, right? So like a bunch of different possibilities was like the most common things. But let's assume, yeah, I want to work now with well, iron. So let's just redo iron. Then I can like add here an adduct, and then say, okay, that's iron. And then here I can define the charge. And then here I can add the mass. And then when I now hit OK, then this would add basically M plus iron 3 plus, right? So that would be a triply charged species. But what I actually need is M plus iron minus 2 protons plus, because that's probably the most observed option. And to create this, I can simply combine them as I need. So therefore, I click on combine here, and then I actually take the iron 3 plus, so M plus iron 3 plus, put it here, and then just take the iron minus the proton and actually add 2 of those. And then I hit add and finish. And then this should appear here in my list as iron plus M plus iron minus 2 protons plus.
But if I want to add like M plus 2H, how
Um,
can I specify the mass difference?
then you would combine and you would use M plus H and M plus H and finish this. And then it should appear as M plus 2H plus. 2 plus, excuse me. Does that make sense? You're muted. You're still muted.
But the mass should be subdivided by 2, right? Because the
Yes.
adduct will not appear as this value. So I want to get like an adduct with plus 2. The mass by itself will be subdivided. So will it be able to get it?
Oh yeah, absolutely. I mean, like it's kind of like naive, right? So it does not like look at actually charge stage depending on isotope pattern or whatsoever, what we could do as well. But it will now simply use this as a possible annotation.
Okay.
And then in comparison to the M plus H plus 1, it needs, of course, to have like the delta of, which would be the half of the mass of the M plus H plus.
Yeah. So another question, when I have two kind of edges, would I be able still to modify the width of the edge based on the cosine score or not?
Yes.
Because I will have like two kind of edges, like one
Yes.
which is dash and one is a solid line.
Yeah. So it gets like a little bit more tricky, especially because the cosine score as well as the correlation score, they are in the same field. So in this case, if you look at my network, which I just like pulled up, you see already that the edges have different width, correct? And how I did this was through the mapper for the edge. And then I used the width function. But then, yeah, you see, like I only made the gradient for the very like first part from 0 to 1, because that was what was interesting for like the cosine. And then like the higher numbers, they're like all from the correlation edges. So yeah, you may need like to get like a little creative and figure those things out. Yeah, so there's a couple of new categories. I mean, ideally, and I mean, that might be something for Ming, or that might be an issue to make on our GitHub, would be to separate those scores into two columns, actually.
Okay, good. Thank you.
All right, does anybody want to share their networks and what they found?
Can I ask a question?
Sure.
Very sure. So yeah, it's very simple. Actually, you guys have any plan to make it possible to look into the ion identity network through the in-browser visualizer? Currently, I can find that it's not visualized in the in-browser visualizer. So
yes, but I want to rebuild the visualizer to be better. There's like a V2 that we're like architecting right now.
So I mean the
it's coming. It's figuring it out.
Okay.
Can I also ask, so why would you not always run this workflow from now on?
I don't know.
Okay.
Wait, from a what, you mean using MZMine to detect ions and things like that?
Yeah, like switch from doing, because our default is to do feature-based networking for almost every data set. So why would we not, is there any reason we shouldn't switch to doing this?
So, I mean, I think it's a question. So if you have to choose between feature-based molecular networking and ion identity networking, I would use ion identity networking, unless you used like a Zuriel DDA setting where you have like an MS1 every 5 seconds or something like that. So your duty cycle needs to be somehow able to produce like a solid chromatogram. But otherwise, yeah, it's a question whether you want to do like classical molecular networking or this, I would say. Another reason which could be, and we're working on this, is that it's not in the main MZMine distribution yet. So if you want to like use other functions, which are in the latest MZMine version, then yeah, you cannot have ion identity networking. So right now we only have like our in-house version, which you downloaded through Robin's GitHub. But hopefully with like the release of MZMine 3, that will be all in the same package.
Yeah, it kind of one of the issues specifically with ion identity networking, and kind of ties in with Kyo Bin's question, is one thing that really made the networks more interpretable is we start doing a bunch of graph topology filtering. So we break up these components into smaller things that are a little bit more digestible. And so now one of the issues is once you add more edges in from ion identity, especially if you're not particularly judicious about the sensitivity of it, is you end up with hairballs again. So it really depends on kind of your sensitivity to that. And so one of the things that is not in place is how to intelligently filter out the network where you have this heterogeneity of edges. Which one do you throw out now? This is actually a kind of a big problem, especially if you throw an ion identity for one polarity, plus you add in the polarity and the cosine, you're kind of in this weird scenario again of there's too many edges and you can't find anything. So that's one of the limitations. There's a balance to be struck. And how do we, on our side, on the feature-based molecular networking side, how do we start dealing with this kind of complexity in kind of a more rigorous fashion? That's an open research problem and kind of a user experience problem that we're just trying to figure out. So that's one side. You don't want to be overloaded with information because that's where we started from, right? You're trading one information for another. But so it really depends on the question you're asking. Do you care about the variety of chemical diversity within one adduct species, or do you really want to collapse it down? And I think kind of Laura Isabel, I think your question is a little bit different than a lot of like natural products people. So it really depends on the kind of group you're looking at. Additionally, as Danny mentioned, there's classical molecular networking, there's feature-based, kind of the original feature-based, I guess it's classical feature-based, anyway, and then there's ion identity. There's like too many things coming around. But it's always a trade-off of complexity. So with kind of classical, is kind of the most extreme case, right? There's just almost no parameter tuning, which is good and bad, right? It like does a good job, but not a great one, depending on your question, if you care about quantification and kind of more redundancy reduction. But then on the other side, with ion identity, as we saw here, do you really want to add more parameters to your life? And so in a lot of cases, you do, depending on your question, but sometimes you're just like, man, I don't want to, deal with that. And so some of the simpler stuff will accomplish what you need. So as we're moving forward, kind of the goals are, can we start auto-tuning some of these things so we reduce parameters for everyone? But at the end of the day, with more complexity yields more things you have, more knobs you have to turn. So it depends on your threshold. It's like there's more power, right? But there's more work. But if that return on investment trade-off matters to you and you can handle that, especially with the same data types coming in with the same parameters, then that's totally what you can do and it's totally fine. But that's kind of my take on these trade-offs. That's why we've developed these tools that seem to compete in some ways, but it really is partitioned into this complexity space of how much work you want to put in to get more payoff. So
I have another question. For some compounds, I don't have the protonated adduct. I just have the ammoniated and sodiated adduct. So ion identity network will be still able to connect these adducts or not?
Yeah, you can define them. So if you have like a weird, I don't know, like delta, you know that your compound class is losing, then you can just like combine those deltas.
Thank you.
Just to add something that I felt yesterday when I was trying that, I felt like if you have a bad chromatography or really small peaks, you will lose them, or at least I felt like I was losing them by doing the amount of filtering.
Yeah, like I totally agree, and that's probably, to come back to the previous question, that is probably one of the, if you are like in that room where you say, yeah, I really want to get like to the maximum information out of my data set. But if you have bad chromatography, that brings limitations. Also, if you want to merge like positive and negative, but you have retention time shifts, then that of course like kind of like brings problems. Either way, you can like adapt for whatever settings you have. And there, I would encourage you to actually like dig through like the settings we were setting up for you in the batch. And just to go quickly back to that. So here, the row grouping and the meta-correlate function basically define that. So for correlation, and here you see, basically a couple of functions. So first of all, minimum sample filters, right? So that has something to do with like, the number of like replicates where a feature needs to be found. So if you only have like one replicate, you probably want to decrease that number. And then, so the key thing is here in the correlation grouping. And there are like basically two settings that are really important, and that is the number of data points and then the correlation score. Right, so if you have like really good correlation, really beautiful chromatography, you may want to like increase the correlation cutoff. But if you have like very poor chromatography, you may want to lower that. And then the same for the data points. So right now we use the setting of minimum 5 data points, which I think is like very little for a chromatographic peak. But yeah, like so in this case we have 5, and it says that it needs to have 2 data points on edge. So that means like on both sides of the apex, you want to have like at least 2 data points. If you now have a duty cycle of, I don't know, 5 seconds, how likely will it be that your UHPLC peaks actually have that number of data points? So adjusting this accordingly to your chromatography, I think is key. I would probably go rather up than down. Yeah. Then,
so the number of data point is correlated with the number of spectra per second, right?
No, it's the total of MS1 spectra that contribute to a peak. So if you have like, for example, a very like long HPLC run, then your duty cycle time might be not so critical. But with like in our case, we have a 10-minute gradient and very narrow peaks, then you want to have actually like a fast scan speed. Does that make sense?
No, I didn't
Then
get it. So,
in the case like if I gonna run the correlation module after the join aligner, then what the model will like calculate the correlation through the multiple sample?
Yes.
Okay.
So
maybe it's a good idea to show the tick plot, the chromatogram plot.
Yes.
And there is a.
Let me just actually execute it then, because I do not have it loaded right now.
So I saw Robin, is it that?
Mm-hmm.
Robin Smith. I saw him. He has some videos on YouTube about those things.
Yes.
About 2 years ago, maybe. I don't know.
Yeah.
Is
We
that
made a
valid,
couple of
right?
tutorials right at the beginning,
Okay.
and they're way more detailed than what we did today. So yeah, definitely make use of them. And
but that's the same version.
I think roughly it should be the same. We simplified some of the settings, so there was some options were removed, which I'm not 100% sure if this is the same as in the videos which are online.
Okay.
But I think roughly the settings are more or less like the same. And again, they're like, if you hover over the fields, there's a short description, and there's also documentation to do that. Okay, just trying to. All right, so just like, yeah, I think it's actually a great idea to like go through some of the exercises. There's also a visualization function in GNPS, so we did not cover that at all. but you can also import, excuse me, in MZMine, you can import the GNPS outputs back into MZMine to visualize networks here, but that's all on a very like beta level. But yeah, there's definitely a lot of things to explore. Yeah, while this is running, is there some other questions, or does somebody want to share, like maybe something they found? No, nobody found any molecules in the hands-on data?
I didn't try.
Come on, like we picked such a nice example. I'm really curious what you found.
It worked for me, but I don't want to spoil the fun for everyone else.
No, come on, tell us. There are multiple, spoiler, there are multiple Siderophores, so you can just tell us one.
Yeah, I mean, I have your cinebactin
Mm-hmm.
plus iron.
Okay. And you have only one or two?
No, I have two. I have 2 years cinebactins plus iron with slightly different retention times.
Okay. And do they have a difference in iron binding?
Well, both look like they're binding.
So if you look at the pie charts, do you see a difference there?
Oh, I didn't do pie charts.
Okay, so the really cool thing with your cinebactin is that we actually have 2 stereoisomers in there, and one seems to bind better than the other. And that becomes especially interesting when we look at other metals. I don't want to spoil too much, but yeah, there's isomer specific like binding efficiency, and that has something to do also with pH because they converge to each other. So that is really cool. But yeah, what other compounds are there? Somebody else? How many people do we have here? Like out of 20?
I was eating pizza. I'm sorry.
All right. I mean, if not, you can like do it later on, and then just we will follow up somewhere in the future workshop if you come again, what you actually found. Okay.
Daniel, why don't we just go over it again then? Like what's
sure.
Like there's a million, it looks like, I don't know, like we want to find anything that has iron bound to it, but there's like,
yeah, so I think like the what Allegra showed you, like that already like highlighted like colors based on different adducts. So that would be like one very straightforward way to look at it. So you could like basically highlight those nodes that actually have like iron bound based on the ion identity, right? So because we identify that adduct, and then I would simply scroll here in Cytoscape to best ion, if I can find it. Here we go.
Yeah, that should be a better way to choose the color.
I know. So I could pre-select the columns, but then I have to go through that anyway. So yeah, and then I can simply, now check all the nodes here that have N plus iron minus 2 protons. And then yeah, like I can highlight them, or like I can simply, I don't know, like pick one that is interesting. So I don't know. Let's try this one. And then hit here. I have to click select node. And then click here the magnifying class. And then it will bring me to that node. And then I can look, oh, does that actually have an annotation? Does not seem to have an annotation. But now I could look at the surrounding nodes, right? Like select all of them and see, oh, maybe my library was actually biased towards the protonated species or whatsoever, and see if like the M+H version has a library ID, but in this case, actually none of those had one. So, but if I want to like now do that thing a little bit more systematic, then I can also just use a mapper and actually highlight all the iron containing nodes based on a certain color. So therefore I could go here to style and then node and yeah, remove that image. If it doesn't let me. And then, well, just use a color mapper to basically use best iron. And then
what is best ion again? What's that mean?
So that's the ion annotation from ion identity networking.
Thanks.
So yeah, I can make them, I don't know, golden. Okay. And then, yeah, I had to remove the pie charts. And then I see already inside of my network now, if I zoom in, which nodes are actually orange, right? And then I would see here, oh, there's an orange one. And here I had another mapper. Let me talk about that really quick. So I also changed the shape of the nodes, whether those had an information in the compound source. So that's kind of like a metadata for like library hits. And I simply said that all that were either commercial accrued, isolated, or lysate, which are the only options for library spectra in there, then make them square, right? So like any node that is a square now should have a library annotation. And what makes this one here in particular interesting is that this is an iron adduct, and it's like next to a node that has an annotation. So, and then I can basically look at this one here and check out what it is.
HBDZTN.
Oh yeah, there we go.
That's crazy.
I would assume that this is probably like a short form of Yersinia Bactin, because what is already striking to me is that the mass is 307, but then we have the M plus iron. Oh, Peter just texted me that he wants to join the workshop, and we have to let him in from the waiting room. Ming, can you do that really quick?
I don't see him in the waiting room. How do I?
I don't know, maybe you have to go to the main room because we're in the breakout room.
We're keeping the boss out.
He was just too late. So yeah, and this example, and then the M plus iron here actually has like the kind of like double. So what that could mean is that I may use two of the concatenated, of the truncated products to actually complex iron. So that's a wild hypothesis. Would be actually now interesting to look at the structure of, what's the name again of it? HC something.
You're saying this because the difference in the edge annotation is 2M plus
yeah, exactly,
iron.
plus iron.
Oh, okay.
Yeah.
Okay. Oh, okay.
So there's, and that's kind of like the level where really this becomes interesting for like a biological information, because that not only tells you, hey, that compound like binds iron, but also, hey, maybe that needs to be a dimer in order to complex iron. And so I think that I love that type of information, that you can pull this now out of like a non-targeted metabolomics data set.
Yeah.
All right, so yeah, please explore and check out if you can like find something interesting in there.
Hey Daniel, in these approaches, when we're changing edges or fill colors, with we're searching for iron, there's maybe like 20 different selections to go from.
Yes.
You know, is there a way where you can just say do all of them that include iron? Is there a way to do that instead of one by one? Like if looking at your screen right now, there's 2M plus iron, minus plus, and then there's another one iron down there, and you do this all individually to all color them individually.
Yeah, that's a good point. So I mean, the first way I showed you, that was like probably the most systematic way. So I sorted the table by the iron annotations, and then I had like this list of I don't know, 8 or so. Another way, if I don't want to like sort the table and directly use a filter option for that, then I can use the select button up here and simply put in node best annotation, if I find it, yeah, best iron, and then say, okay, it needs to contain iron, right? And then I would already highlight them all in the network, so then they would be blue. But yeah, that's, so we're really like at the visualization part here. So that's, I mean, it's data exploration. There is no right or wrong, and there is probably many different ways in order to prioritize this within Cytoscape.
Thanks, that's great to see that option.
What I personally also like to do is that I import like the table into R or something, and then also make my own columns based on what I want to visualize. But I just also have columns that like note, label, or coloring, and then I can just say, or shape, and then I can just define settings on those columns.
Yeah.
Because you can really easily also import your own table as long as you associate with either a node identifier or an edge connection.
Hey, Dan, maybe you don't show your screen.
Ming, did it work out?
I have a question then. Yes. So if you can I like if I stop by any edge, is it easy to identify what is the type of connectivity between both?
What do you mean in terms of like delta mass?
I mean like these dashed lines means it could be sodiated, ammoniated, whatever adduct. But how can I distinguish between different adducts if I want just to identify what is this type of connectivity?
So it's actually
the same.
It's in the Cytoscape. So if you look at the edge attributes, it'll tell you that it's an ion identity edge, and there's also a description. So that description should tell you what the delta is. If you care about like the assigned species of it, then that's in the node attributes.
Yeah. So if we go back to Cytoscape, and go to style, and I assume that in the edge table, first of all, there is an edge annotation. So instead of like displaying a delta mass, I can already like display actually an explanation of this delta mass. And to like visualize this, I would go to edge, and then so edge under style, and then go to label, and then use edge annotation. And then in theory, this should now add the information onto the edges. So yeah, here basically we have a delta of 21, and that means that one of them was likely M plus H plus, and the other one M plus sodium.
Yeah, this is exactly what I mean. Yeah. Thank you.
Yeah, but you have to be careful, right? They also could be the protonated and sodiated version of an in-source fragment or something like that. So there is a couple of combinations that would actually like allow for such a delta. So that's not absolute. The same applies. I don't know if we have some here.
So if I
Yeah,
have in-source
see,
fragments like deglucosylated, for example, fragment, could I add this adduct or just like ion species?
say what
I mean,
that?
sometimes like if I have a glucoside, it fragments and like at the source, and it shows the glycone at the same retention time, which is not a different feature. It's the same feature, just it's inside
yeah,
of fragmentation.
you can define this delta. Yeah. You can define this delta for like the neutral loss system.
Okay.
All right.
Daniel, I don't want to hijack the thread, but do you want, since I think we have some time here, can you comment on your idea of using this for finding isotope logs?
Yeah. So if you used MZMine before and you used the de-isotoper, then that's a great module. It's very simple. You just like define a retention time and mass tolerance, and then it will like combine basically all the isotopologs. But that only works very well if you either use like a wide mass window, or you are just like looking at standard compounds which mainly have 13C isotopes. So now if you look for like, let's say, brominated versions which have like a different mass defect, and hence like a fine isotope pattern. So I don't know, are you like all familiar with like fine isotopes?
Yeah, I mean, I primarily have been using camera and some of the stuff out of Formularity to do this, and I was just wondering how this compared to those two tools.
So camera does like a very similar thing. So camera also looks.
Have you compared it directly? I'm just curious.
So we didn't really benchmark it.
Okay.
Camera is actually used in XCMS to do ion identity networking now.
Yeah.
So we interfaced it to existing modules such as camera. I don't know for MS dial. So yeah, we didn't also. Thanks a lot for bringing this up. There's a couple of different ways to do ion identity networking. So there's other correlation modules and other feature finding tools, and they all interface now to that additional edge format, so you can actually perform the final ion identity molecular networking in GNPS. And yeah, one of those would be camera. And what you can do there is simply you can like define the exact mass of like isotopes, and you can like play this at the resolution that you actually need in order to resolve that fine isotope pattern, which was like the current de-isotoper in MZMine was not possible. So now that's something you can do already if you just like add like an isotope as a delta. But the idea is, and we actually just got like a Google Summer of Code project funded for that, which is really cool. So Lukasz, I think a very talented student from Poland, is trying now to incorporate a fine isotope grouper into MZMine, and that will have like 2 iterations. First, like a simple one, which just like looks at like general, like retention time windows and does not do any correlation analysis, but where you can like user specify exact mass deltas for isotopes. And then the next iteration will be then one based on ion identity networking, which I think makes sense. So it's stay tuned. I think it's going to take a little while, but
yeah, no, of course,
we're working on that.
Of course, I was just wondering to see what the differences were, the similarities across the different options. Thanks.
Yeah, I think like camera also does do Pearson correlation, right?
I do not remember off the top of my head.
So yeah, I think they're fairly, so they're, yeah, I think they should be fairly similar, but it would be great to actually benchmark.
Yeah, just curious. Thank you.
All All right, more questions or results you want to share? Now's the time. Cool. Well, then, yeah, thanks so much for stopping by. I hope that was useful, and I hope you're gonna try it for your own data analysis. We have extensive documentation also for ion identity networking on the general GNPS documentation page. So feel free to take a look at that. Then Robin has made a couple of very detailed videos about ion identity networking with MZMine. And we will also have a recording from this workshop online. And yeah, if you have if that does not cover your needs, just shoot us an email or I don't know, post it in the GNPS forum. There's multiple ways to get in contact. Also, if you have good experience, it would be good to get feedback. Hey, we found something exciting with it. Cool. Well, thanks a lot. Ming, do you have some things you want to say before we leave?
No? Wait, okay. For those of you who are interested in the tools and the platform and all that stuff, you can ask us on the forum, send us emails, or tweet at us. Maybe tweeting is the most effective. Anyway, but we're happy to answer questions. It's one of those things we don't know what we're doing, so you can help us figure out what we're doing and where we're going wrong. Laura Isabel knows. We've been working together for a while, and she's like, do this. It's like, okay. So honestly, it's one of those things. It's it's a community, and any help, any criticisms, suggestions, as well as contributions to the documentation are very much appreciated. It's all on GitHub, so just make a pull request, just make an edit and do a pull request. So super simple. It's like editing Wikipedia. I don't know if you've all ever done that. Anyway, thank you for stopping by. And I didn't actually do anything, so thank Danny, Allegra, and Robin for actually organizing it. So,
hey, last question. There's something tomorrow, right? Is there a workshop? What's the next one?
So, oh yeah, for the future, look at. So there's a small kind of a presentation by a kind of a friend. Actually, he's the brother of one of the people in Peter's lab, Scott Jarmusch. So he'll be giving just a small thing about how they've applied GNPS to natural products, but it won't be a workshop. Next week, let me check. I don't remember anymore. So next week we have a quick workshop on GCMS. That's next week? Okay. And following that is this chemical directionality work with Danny. So this is more on looking at longitudinal data and trying to find patterns in that in relation to the network. So
what it basically adds is like a direction. So very straightforward thing. So right now, a molecular network is static. We just know, okay, those are all the things we find. But what actually is a very interesting question we're often after is, how do things change over time? So we now try to draw arrows within that networks and say, hey, over my, I don't know, phytoplankton plume, that compound may gets converted into that other compound. So yeah, looking forward for that too.
Nice.
All right, then nice seeing you all.
Can I ask you one thing?
Sure.
Can I ask one thing about MZMine? Maybe you can help. Can I export a CSV file with the MS1 chromatograms?
Not that I know of, but that would be actually really cool. So you mean as a small, as all data points, or as
no, just a matrix of MS1 from a defined MZ range as an Excel file.
Okay, so you can export a couple of things. I don't think that you can export all data points. So when you are, let me see. When you go to MZMine, click the latest peak list, and then go to peak list methods, export, and you can export this to a CSV file. Right? Then you can actually check here like all sorts of like different things, like width of your peak, start time, end time. So there's a lot of like information you can pull out, but I don't think that you can export all data points. But that might be the
It's
question.
like you select all your data and you plot the TIC, and then you just export that as a
Exactly. So normally what we do is simply I want the ID, that would be the scan number, then MZ value, retention time, and then I typically take just the peak area. But now in addition to that information, I could also export others like the peak height or the peak duration. And then I would basically just get new columns, which would then tell me, oh, like those peaks had that width, something like that, which may important for you to like evaluate your chromatography performance or something like that. Yeah, data points. If you don't know what setting to use for the correlation module, you could have also checked the data points. So there's a couple of things, but I don't think that it exports like the full XIC with like every scan as a data point. If you have their particular needs, make a comment in the MZMine GitHub. So yeah, they're very active as well and probably know better than we do.
Okay.
All right.
All right. Thank you.
Do you think I could just ask a question?
Sure.
Just before you go. So just to see if I got the point of this. So we're looking at this big sprawling network, which has two Yersinia Bactin annotations in it, right?
Mm-hmm.
And then we have this HPTZTN thing, which I see was like, that was discovered a year ago. And so that's not what you've discovered in this study.
No.
And so I guess there's another couple of nodes here that also have like iron adducts, which have been linked. Which aren't...
So you can scoop us now by writing a paper about that.
Well, is that what you wanted us to see?
Well, I mean, to be completely honest, we have like a paper under review on that, but it's not for iron binding. So
oh, no?
We didn't show you the most exciting metal binders.
Ah, okay.
But if you want, it's probably gonna get out as a preprint soon. So I can probably already tell you. Yeah, it's a very good sync binder as well.
Oh, cool. Okay.
And that was kind of like unexpected.
Right. So
because
if we
there were a couple of papers describing it not to bind sync, but then we showed that it actually does bind sync.
Right. Okay. So if we were to go back into MZMine and go into the ion identity network and add zinc in as an ion, then we could map that and see what the ones that you're talking about?
Probably not, because those samples were only the ones from the iron addition experiments. So you would need to scroll through massive, and I'm sure that data is also public, so you can find it already there to find the actual data with the sync addition.
Okay, thanks.
Cool.
Guys, thank you very much. It was really amazing. Thank you. You really rock. Really. Thank you.
Thanks. All right. See you, everybody.
Thank you.
Thank you.